Hello AP Chem. In this video we're going to review a little bit more about solutions, whether they're aqueous or non-aqueous, some math a little bit involved, and some other qualities about solutions. So when we make solutions, the solution process, you can dissolve things at a different rate. And those same substances may not dissolve at the same rate all the time. So there are a lot of things that will affect the rate of dissolving, but in general, more collisions or more energetic collisions mean a faster rate of dissolving. So the first factor that affects the solution process is surface area. More surface area, which means smaller particles, means a faster dissolution rate or formation of solution. Because small surface area or small particles mean a larger surface area, that means there are more solute particles, the ones on the surface, that are exposed, that they can collide with solvent particles to be dissolved. Agitation or stirring also increases the rate. This allows fresh solvent molecules to come into contact with solute particles. So when we dissolve something, for example, if we were to dissolve something in water, those water molecules that do the dissolving, that surround a particle, they become occupied, okay? They can only dissolve or surround one particle. If we keep putting in fresh particles, water particles that are not associated with a particle yet for the solute, then we can increase the rate of solution forming. Temperature is also something that will affect the rate. It will also affect how much you can actually dissolve, which we'll talk about a little bit later in terms of solubility. In general, a higher temperature means a higher average kinetic energy, which means to a higher rate of dissolving. One exception would be gases. So to dissolve gases, if we increase the temperature, then those gases can escape into the atmosphere out of the system. So we have less dissolved there in some instances. But in general, higher temperature means higher average kinetic energy of water particles, which means there are more faster and stronger effective collisions. And it, again, not only affects the rate, but also how much solute you can actually dissolve. So saturation kind of relates to how much solute can be dissolved. So if you think of dissolving like a partner type of dance, when a particle is dissolved, it's surrounded by solvent molecules such as water molecules. And that particle remains dissolved in the dissolved state as long as those solvent molecules surround it. Those solvent molecules that are surrounding it can only dance with one solute molecule or particle at a time. So when all the solvent molecules are occupied, the solution is going to be saturated, meaning it can no longer dissolve any other substance anymore. When solvent molecules aren't, so solvent molecules in general, it's not just like you're going to homecoming with a date or anything like that and you are exclusive. Solvent molecules dance with other solutes, so it's not just one particle the whole time. They can switch particles that they are dissolving. So within a saturated solution, we have two processes occurring: dissolving and recrystallization. So dissolving is going from, for example, having solid salt crystals being dissolved into an aqueous solution, and recrystallization is having those aqueous ions from the salt going back into the solid state. So if you have a cup of water with salt in it, you keep pouring salt until eventually you have some solid particles at the bottom. That particle is not staying the same ions the whole time. The water molecules are kind of trading off partners. Sometimes the ions are in the aqueous state, and sometimes they're in the solid state. So when the rates of these two are equal, we have a saturated solution because at all times water molecules are occupied, even if it's not with the same particle the whole time. In a saturated solution, even if we add more solids, it will not dissolve anymore. So if you keep adding salt to that solution, you're just going to have more solid piling up at the bottom. It remains saturated, but you just have more particles that are in the solid state. An unsaturated solution contains less than the maximum amount of particles that will dissolve. So you can add a little bit more solid and it will dissolve into the solution. You also have something called supersaturated that we'll go into later, but you can make a supersaturated solution, which means it contains more solute particles than its regular saturation point, and you do that by heating the solution and then slowly letting it return to room temperature. Your solution, those solute particles remain in a solution in the aqueous phase, but you have a supersaturated solution. So we'll talk about that a little bit more later on in the year. So solubility, thrown around this word a little bit, but it basically describes the ability of a substance to dissolve. How easy is it to dissolve? The technical definition, because it is a measurement of something, is the amount of substance that is required to form a saturated solution in a given amount of solvent at a specified temperature. So typically it's given as grams of solute, what you're dissolving, per 100 grams of solvent at a specific temperature, so like at 20 degrees Celsius. Because the solubility of a substance at 20 degrees Celsius is going to be different than the solubility of a substance at 100 degrees Celsius. For gases, there's also like solubility of gases. It's going to vary not only with temperature, but also pressure. So for gases, you have to define the temperature that you are describing and the pressure, what condition surrounds this dissolving of gas. Usually, but not always, solubility increases with temperature. Solubility curves show your solubility in grams of solute per 100 grams of solvent. In this case, it's in H2O, versus temperature. So again, solubility depends on temperature. So for salts, you can see that we have graphed the solubility of potassium iodide at 10 degrees Celsius, 20, 30, 40, and you form this curve. Some look more curvy than linear, some look more linear, but it's still called a curve. We can use the solubility curve to determine if a solution is saturated or unsaturated. So, for example, sticking with potassium iodide, if I have a solution of potassium iodide at, let's say, 15 degrees Celsius, and I have 135 grams of potassium iodide dissolved, I want to know, is my solution saturated, unsaturated, or supersaturated? So then I said 15 degrees Celsius, I go to 15, I look for potassium iodide, and I go to 135, and we hit about there, the middle of that square. Okay, so the middle of that square, right here, is lower than the curve shown for potassium iodide. So that means, under these conditions, I have an unsaturated solution. I can increase the number of grams of potassium iodide and still dissolve potassium iodide. If I go to 20 degrees Celsius and I have, we'll say 143 grams, that's about here, I am right on that line. That means that the solution is saturated. If I am at, we'll again do 15, and I say I have 145 grams dissolved, that's above the line, so it is supersaturated. So anything under a given line will be unsaturated, anything on the line will be saturated, anything above the line will be supersaturated. Solutions change the colligative properties of the solvent that they are dissolved in. So all of this should say solvent, not solute, sorry. So cross that out, not solute, solvent. So for example, they tend to lower the vapor pressure of the original solvent, for example, water. So if you have water and you add salt, the vapor pressure of water is reduced because those water molecules that would be escaping into the gaseous phase are attracted to these ions that are released into the solution. So it's kind of like those water molecules that would escape are distracted, so they stay in solution, which means there's lower vapor pressure. Less molecules are going out into the gaseous phase. They also tend to lower freezing point of the solvent. So again, when it snows and the roads get icy, you notice that cities put salt on the roads. That salt makes a water-salt solution. Because salt water has a lower freezing point, it has to be even colder for ice to form. So it melts the ice on the roads, making it safer to drive because it's safer to drive on water than on ice. On the opposite end, it tends to raise the boiling point of that solvent. So if you're boiling water and you add salt, the water is going to be hotter than 100 degrees Celsius when it actually boils. Okay?